questions of anything, like the most recent homeworks? I'm gonna start with, I think is the most recent homework assignment, and just pick up from there, take off from there. So that was the force that depended on the explicit time. Is that the last thing we have figured out? What do you guys have there? E to the minus alpha t, that force.
Something about integrating piece of t in order to get x.
Perfect, yeah, so that, okay, we're on the right place. So let's have a look at this once again. So we're starting to integrate Newton's laws of motion for a point particle, essentially, for one single mass. And I'll go ahead and write this out here, what we're doing for the next several weeks in one form or another. We have mass, and we're doing it in one dimension. So the two dots, have we already gotten accustomed to dots? Two time derivatives equals a force, understood to be the net force. Position, velocity, and time. Can be all three of those, or it can be just one of those. And the example we started with, and I'll just continue to discuss for a moment. You guys have it in front of you, you can correct any mishaps I have here. So the example was F is equal to, I don't know if I put a subscript on it last time, there's a constant, and then e to the minus alpha t. We're going to take alpha positive greater than or equal to 0, t greater than or equal to 0. And at the time we didn't do that, but maybe a good idea to graph f of t. Because we're big on being able to visualize everything that we're using. Okay, so there's the e to the minus alpha t. So the integration of this was now dv dt, because that's the first, yeah, okay. I'm going to use these interchangeably, was equal to this f naught e to the minus alpha t, and then we integrated it, we got d minus d0 integral f naught e to the minus alpha. I'm saying t prime because the argument e is there. So if we do this, we actually get that result we had last time. B of t is equal to d naught, I believe it was f naught over m alpha 1 minus e to the minus alpha t. Is that what we had? Yeah. So this thing's already worth discussing. It's non-trivial anymore. And we found that we have to be able to take the limit alpha goes to 0 in one shape or another. We just used L'Hopital's rule last time. You can also do Taylor expansions up here, get the same result. But we found that the limit is all right with limit alpha goes to 0, b of t, which is v naught plus f naught over m times t, which we just recognize as the constant acceleration solution. So this process is really important to actually see what it is you have here. You know, we're not plugging numbers in, nobody's asking us what some value is. We're looking for the functional form of this thing. What if we had to graph this? What if we had to graph b of t, and at t equals 0, we had this positive b0. What's this graph going to do? Anybody? Pardon? It depends. This one is going to be a straight line, right? The limit, actually, how about I do that as, I'll just kind of do this in a dotted line. we would have that. But how about this graph here? This one's got a little trickiness to it. And what we have to realize is as t goes to infinity, this just goes to v naught plus f naught over m alpha, which is another constant. And so apparently it's going to somehow go up against this thing asymptotically. And I'm going to argue that this is what constitutes an actual understanding of this solution, as opposed to just having found it and then write it down as our own. So yeah, we want to be able to analyze all of these solutions and see what they're really doing. And that'll bring us to that homework assignment, which I think will fit right here. So what we want to do, and I'm just repeating what's in your notes right now, maybe I'm adding a little detail. What we want to do is find, by integration, x of t is the integral v, in fact, we'll have x minus x naught will be this integral v of t dt from 0 to t, so this prime means it's just an integration variable. And you can see that it's right. T is equal to 0, I just have x equals x naught, the way it has to be. And you're going to plug this in here, including the v naught, by the way. You have to plug all this in here, carefully integrate it up, carefully evaluate 0 to t, so you'll get one result, and then we're interested in that same limit. So check t equals 0, t goes to infinity, and then also find limit x of t, alpha goes to 0. Same thing we did for b. Question? It is. I'm just rewriting it. We haven't done it yet. I'm just discussing it more. Yeah, this is exactly what we had there. Yeah. Oh, and I want to add to this, include, so in what you turn in, you want to include the whole discussion. Right? Don't want to just start where I left off, but quickly run through this, right, draw it out. And that should give you a really nice understanding, because, so include v of t derivation or calculation. Because what we found was we're getting the constant acceleration as a limiting case. And that's the free fall case, essentially. And we're going to keep going along those lines. Good, so that was that homework problem. Later on, we'll discuss which ones are this week and which ones are next week. We're never quite sure. Is the list pretty long already?
About 4 for this week so far.
Okay. So I'm going to add another example to this mix. And all of these examples, we can take a limit and get the constant acceleration physics back again, which is really essential there for us to understand. So this first example is kind of contrived. Okay, who has an exponentially decreasing force pushing something, but it had good, important limiting discussion. This next example is very physical. So we want to do fall with friction. So friction's always present when you have air, say, and you drop something. Okay, so this is a very realistic example. And we're going to do this one. So we've got our M force is going to be mg minus k times velocity. And the first thing you'll notice here, I decided to choose the positive direction as down. Otherwise I would have put minus mg, but I can do that. Okay. So, note positive direction is down. So the first thing we do is note that this force here, F, is equal to F of x dot, we could say, right? This is a force that depends on the velocity, and we're going to write it dv dt. I'm going to divide both sides by m. dv dt is equal to g minus k over m v. Okay, so now this is going to require a little more technique than just integrating something up. And what we'll do is use the technique called separation of variables. So solution by separation of variables. The occurs to be. We can actually analyze this thing for a moment before we even start to solve it. That's another lesson. You want to actually have a look at this thing before you attempt to solve it. And what I'm driving at here is if the right side vanishes, then the left side is constant. And that's another way of saying there's a terminal velocity involved in this problem. So I'll put that as a note. dv dt equals 0 when v equals mg divided by k. And that would be the terminal speed. When you drop something, it doesn't just keep accelerating. Say a feather obviously, but even a piece of paper or something. Terminal speed. Skydivers reach terminal speed too. Anybody ever done skydiving here? I haven't either, but there was a chance somebody would have done that. They reach a terminal speed, at which point they're, I'm told it's around 100 miles an hour. But you see that right here. We'll get this, so I'll call this VT terminal speed. So that's something we'll be able to find when we solve the problem. It has to be part of the solution. So here we go. The separation of variables technique, and definitely we use this D or delta notation. We're going to bring all the V's to one side, the T's to the other, and integrate both sides. When we're done, we can take our solution and make sure it's a solution by plugging it back into the differential equation. So we integrate both sides. This one we'll just let t start at 0. So this one is trivial. This one here, we go v0 to v. So now we're actually faced with an integration that we have to do. And we're going to have a natural log. So I'll start with natural log of g minus kb over m. I take that derivative, I get 1 over g minus kb over m. The interderivative is minus k over m, so I'll have minus m divided by k natural log v naught to v is going to be equal to t. And we'll just work on this for a couple of steps to get the proper form. So we're going to multiply by k over m. Okay, so we have natural log of g minus k over mv. This is, we could call this prime. It's the integration variable. It's going to be minus kt over m. This is the actual combination that's interesting. KT over M, not T alone. And the next thing we're going to do let's see. I want to bring this into a good form before we exponentiate. Yes. So to avoid having dimensional quantities, what we can do is this. We can write the natural log G minus K V over M divided by G minus K V naught over M equals minus KT over M. See, so now I have a dimensionless quantity in there. This is a better way to do it, and I can keep working on this for a moment. What I'm going to do is mg over k, so multiplied by everywhere. And then I'll just have the v's isolated. So that's what we'll do next. Run this over here. And once we get the solution, we have to test the whole thing out. So let's see, we have natural log of mq over k minus v. Divided by mg over k minus v naught. And leave a lot of room here, minus kt over m, because we want to exponentiate this whole thing. E to the this, e to the this, and then see what comes out. So we'll have, so, no, that's unclear, exponentiate. Let's see what came out here. So we ended up with k minus d is equal to mq over k minus d naught times e to the minus kt over m. Now we have to put this into a form that is transparent to us. Right? That makes some sense. We're just going to solve for v here and see what happens. So I think the result that we're looking for is going to be v t equals mg divided by k plus v naught minus mg divided by k e to the minus kt over m. Looks, I think that's right. Okay, put thoughts around this. What you'll notice is just adding that little friction term has given us something that is a bit out there in terms of being complicated. Okay. So you get this complicated result and you have to analyze it to see if it really makes sense. I can't just look at this, well I've seen it before, but otherwise you can't just look at this and somehow see everything that's going on, right? So what about the analysis of this thing? What was the first thing we did on the other one? We were checking the solution. T is equal to 0. So T is equal to 0, here we get a 1. Mg over K plus V naught minus Mg over K. So V is equal to V naught, right? So that one checks out. T is equal to 0. V is equal to V0. So we're good with that. What about the limit as T goes to infinity? This one's interesting. this thing. T goes to infinity. V equals mg over k. So where have we seen that before? Right, 10 minutes ago. Right? We saw that was the terminal speed. So as this thing is falling in the medium with friction, it reaches a terminal speed as t goes to infinity. And because of the nature of the exponential, that could be shorter or longer. It depends on this combination here. So I'm going to put a speed and what controls that is this kt over m. So let's just look at this combination kt over m, or actually, let's just study this for a moment. E to the minus kt over m. Because there's even a lot of physics in here. I'll graph this. One, what does this function do? E to the minus x, so to speak, right? So it goes down like this. What'll make it decrease faster? Pardon?
Higher K, for example.
Larger k or
Lower M.
smaller m. And larger k means more higher frictional coefficient. Lower m means less inertia. Right? So this makes sense. So you drop the feather as opposed to an equivalently shaped piece of metal, right? The metal will go faster than the feather. And what would make this thing decay much slower, right? Is just the inverse of that. To make it decay much slower, we could have either a smaller frictional coefficient or just a much larger mass. Okay? So it's this ratio where there's quite a bit of physics involved. Again, that's the frictional coefficient, that's the inertia, that's the mass in the problem. So it's that combination that tells us when we're in the free fall regime. And of course that brings us up to, when do we get free fall out of this again? We're again going to have to take the limit as k goes to 0 to get free fall. So 0.3 right here would be limit k goes to 0 via t equals. Should I do that or should I leave that up to you guys? Oh, what do we expect to get? What do we expect to get? The free fall would be v naught plus gt, because we were, question mark here, because we were taking the positive directly down, v naught plus t times t. So there's the question about that as well. If I answer that, then I'll have you guys find the x of t. X of t is less fun on this one, it's just more than on the other one. But we should do it. I think I'll assign it. Maybe it'll be on the next week's one. Good, go ahead and erase this. And we'll go ahead and try that limit. Now there's another way to do this limit. Limit v of t as k goes to 0. And what we're going to do this time is expand the exponential into the first order. So what we're going to get is v of t, I'll just put an approximation sign, mg over k plus v naught minus mg over k. And the first non-trivial term here, we're going to have 1 minus kt over m. That's the linear approximation to the Taylor expansion. Linear approximation, Taylor expansion to the exponential, which goes as 1 plus x, and x is minus kt over m. So now we have to multiply this out. So we have mg over k plus v naught minus mg over k. That takes care of the 1. Then we have minus v naught kt over m. Minus times minus is plus mg kt over km. So that was our approximation as k goes to 0. And here's what happened. These two drop out. As k goes to 0, this one goes away. And limit v of t, k goes to 0, indeed turns into v naught. And here you see the k cancels and m cancels, plus gt. So again, we're satisfied that this complicated looking result actually is just free fall. Right? It has all the interesting limiting cases. I'm going to add this next one to the homework as well. So we've done this analysis. We've done this limit. This next one makes you do a little more work. But at least it's not has nothing contrived about it. So here, integrate this v of t above here to obtain x minus x naught equals integral v of t prime dt prime. And you have to make sure both of these are under the integral. This will just give you a constant times t, right? Since these are just constants, it's really just the integration of this. It's going to bring you another m over k. And you have to make sure always that you evaluate the lower boundary as well. Otherwise, you'll have plus some undetermined constant, which can be tedious to figure out. If you go from 0 to t, you actually have everything there right in front of you in terms of the integration constants. And so you'll do that, and the same as last time, you'll check some interesting limits. Check t equals 0, t goes to infinity. T equals 0 is fine, right? You know you're going to get this. What's going to happen here for t goes to infinity, do you guys think? Really erasing. Fall with friction for t goes to infinity. Remember, you're going to reach that terminal speed, and if you reach a terminal speed, then your time dependence just is linear as t goes to infinity. You're left with a linear time dependence. And that'll probably be the one that when you integrate this up, you'll get a linear time dependence. Good. T goes to infinity. You know what? I'm just going to put here k goes to 0 as well. But we have expectations on these. K goes to 0, it's got to be the free fall result. So this one I'll say, this one I'll point out, we should end up with x equals x naught plus v naught t plus 1/2 gt squared. So we know what to expect, and that's how we can check whether our work was correct or not. Okay. done so far. We've done F equals F of t explicitly, and that was F equals F naught e to the minus alpha t. We've done F equals F of x dot, which is this argument here. F was equal to minus k x dot. So that's what we just did. Another interesting one would be F equals F of x dot. Here we would do F equals minus, I'm going to use the same letter, different dimensions, minus k b squared. So this one was minus kb. Maybe I'll use the letter b. This did not have the same letter. And they're both for fall with friction. What's the difference between these two? Have you ever heard about the difference between these two? One is proportional to b, one is proportional to b squared. Roughly speaking, this is the one for high speeds. This is why your gas mileage decreases when you're going really fast. Mileage or gas decreases when you're going really fast. Because the law of friction is not just a simple one for all speeds. And I can do a little physics discussion between these two now. Now that we've done, we've done enough math on this. So yeah, this is linear friction, this is quadratic friction. It doesn't end here, it could have other dependents as well. Also, these friction laws will depend on the shape of the object, so it gets pretty complicated if you're an engineer, say an aeronautical engineer. But you may have even heard where some of these come from. Have you guys heard of the Millikan oil drop experiment? Everybody's heard of the Millikan oil drop? Not yet? Okay, how about you guys? Kind of, sort of? No? They don't teach that in chemistry? It's a famous one. Yeah, we'll talk about that now. We got plenty of time. This is a really important one. The charge of the electron was determined by following the motion of little charged drops of oil as they fell through the air. And I actually did that once. It was a lab when I was studying physics. It gave you a headache looking through a little telescope following these little oil drops up and down. But the point is, the little oil drop reached terminal speed, right, as it's falling through the air, and then it had electric charge on it, so you could dial in a little electric field and bring it to a stop. And Millikan did this, and he did it in such a sensitive way that he saw that the charge was quantized. And so down at Caltech, he's the guy who measured the charge of the electron for the first time. That's the Millikan oil drop experiment. And he actually had to use this law here. He had to know this law of friction for slow speeds as opposed to this law of friction for high speeds. So let me erase this and put something here in your notes. This is something you could look up. Pretty interesting. So, this is a linear law. This is a quadratic law of friction. I'll just put here for slow speeds, and this is for higher speeds. So there's a law called Stokes' law. I'll just put here Stokes. And it's for the motion of a sphere through a viscous fluid. Motion of a sphere through a viscous fluid. viscosity of a fluid is how thick it is, how much internal friction it has. Oil you put in your car has a certain viscosity level. So here's the force law. This is the frictional force. 6 pi eta r v. And I'll just label what these things are. This is the coefficient of viscosity, Greek letter eta. This is the radius of the sphere. And this is its speed, obviously. Okay. So you actually have a measure to find the terminal speed, because apparently this K that we had V terminal was equal to just, what do we have, mg over K, right? Mg over K. So what do we have here with Stokes' law? Mg over 6 pi eta RV. V, just 6 pi eta radius. And okay, a bunch of letters there. Does it make sense? More massive, higher terminal speed, less viscosity, higher terminal speed. And the limit as this goes to 0, infinite terminal speed, slowing down. Here's a very interesting thing we can do with this though. Now the mass is going to be 4/3 radius pi r cubed times the density. Okay. I'm going to replace the mass. I'll do this like this for the moment. 4/3 pi radius cubed times the density times g, and then we'll do the rest of the arithmetic. 6 pi eta r. Okay, so if we clean this up, pi goes away. We have 4 over 18, which is 2 over 9. I'll put the rho and the g and the eta. Those are a bunch of factors. They should make sense. What about the power that's left over? R squared. Okay, so what's significant about this is it explains why tiny drops fall so slowly. Okay. If you have a mister, you know, you spray something in the air and you just see the drops fall really slowly because they're so small. And so people who study, say, sedimentation, they could use this formula to figure out how long it takes for things to, you know, fall through fluid and deposit on the floor and so forth. So yeah, there's your terminal speed. And Millikan had to use this. He needed to know the density of air, the density of his oil drops, G, to estimate, you know, he needed a couple of measurements to get all these estimates. The R didn't just fall into his lap. In fact, I think what you do is you solve for the size of the oil drop and therefore its mass by using this, and then you dial in your electric field and figure out the charge on it. Okay. So I'm going to put here as a note as well, Millikan oil drop experiment. Oil drop experiment. And so this formula here was all for slow speeds. In fact, I've derived this. I taught the fluid mechanics course and actually had to go back and derive this. And it's a huge derivation, and it itself is just an approximation. Just an approximation. It's the linear approximation. You know, I think we'll end with a little more discussion of this, because this is a good physics discussion right here. And I'm coming back to this, right? This was the linear one we just worked on. And now now we've got this quadratic one. But isn't there just one law of nature? So why is it linear and then quadratic? Okay, let's take a quick look at that. So we've been doing Taylor expansions over in math methods. How are you on Taylor expansions? Good, fantastic. So what we'll talk about here is the law of friction. Law of friction in a fluid. And the law of friction in a fluid would be if V equals 0, no frictional force. Unlike the friction we learned about from something sliding on a table. You know, you slide something on a table, you could pull on it for a while, it doesn't move, and so there's a frictional force. But in a fluid, if you push on something, it moves. Okay? So if V is equal to 0, there's no frictional force. So let's go ahead and say we have f of v as a function of v. We already know that it starts at the origin. Okay? So let's go ahead and expand f of v into Taylor series. So f of v is equal to f of 0 plus f prime of 0 v plus 1/2 f double prime of 0 v squared. So suppose there's a law like that, and apparently we've got our 0 here, so the first non-zero term is a linear term. Now there's no proof that it has to be linear. This could be the next first non-linear term, except when you do the calculation, you find a linear term. So for that reason, our function is going to start out linear. But if there's a quadratic term, it's going to take over at higher speeds. That's just the nature, a linear approximation and a quadratic approximation. So we can say, good, the force law actually, the frictional force law, let me start with a slightly different slope. Good, so here's that linear law, and the actual law could go like this. And therefore, for slow speed, for low speeds, you're linear and then you're going quadratic. And this would be the regime that we've tested, and Stokes' law holds, and then higher speeds could be quadratic, and so forth. So yeah, we get a nice and then in the case of a viscous fluid, it turns out that it's 6 pi beta r v, and then plus other stuff as well. So this is actually from fluid mechanics. If you have a sphere, and it itself is an approximation, so it can be pretty intense to figure these things out. But there you have it. So we're going to go next with this. Maybe one more of these velocity dependent ones. Like maybe we should calculate, I'll set it up. We don't have enough time to finish it. I'll set up this squared law now. We've seen some physics. So yeah, we can have m dv dt. We'll make the positive direction down again equals mg minus b times b squared is equal to g b divided by m b squared. You see what's dynamically significant is going to be this ratio. And the same thing is going to happen we'll leave it at that right now for today. So the last thing we'll discuss is what's due on Friday. Somebody remind me what those first four problems were.
First one was calculating range.
Range of the projectile, good.
Second one is near orbital speed. Third one is, honestly, I'm not sure what the third one was asking. Something about r sub t equaling x of t I hat plus y sub t j hat, and then finding derivatives for that.
Oh, that was a curve?
I wasn't sure what it was asking, so I haven't done it yet.
This Y of K thing? This one here on the top of your page?
In green, I covered it.
Yes, yes. Okay, we have a minute or two, let's talk about that one. And then what comes after that?
After that, there's, find it. After that, there's the one integrating dx minus x naught for d, e minus alpha t1.
Good, we'll put a line, we'll make that the assignment, okay, and the other ones we'll put on next week's. That'll be fair. And yeah, I wanna talk about this before we leave. This problem with that curve, this is a good one. Let's do a quick sketch of this thing. So the idea is, we have found the local curvature or the second derivative of a curve that goes through, that nests with the circle. Okay. Y of x equals 1/2 1 over r, that's the second derivative, this is from a Taylor expansion, x squared, right? So what we want to do on this homework problem is imagine we're running through this on our little roller coaster or whatever. We're running through there and we want to find the acceleration. So what we have here is a parametrization of this curve. We're looking at the curve just in the neighborhood here, because that's what we're going to inspect. Okay. And what we have is r of t. I'll write it, okay, the way I had before, it's x of t I hat plus y of t j hat, right? That's just a parametrization, and we want to find b is equal to dr dt, and a is equal to dv dt. So that's just a question of chain rule, or taking time derivatives. What we have here though is r of t is equal to x of t I hat plus 1/2 1 over r x of t squared j hat. And what you're going to find if you take both derivatives, this one's going to expand out a bit because of the chain rule, but if you evaluate this derivative, this is really the punchline. If you evaluate this acceleration at x equals 0, you're going to get the famous b squared over r. Okay. So I'll put here, show that a sub y evaluated at x equals 0 is equal to b squared over r, which of course is a very important formula. And this problem ties together all kinds of interesting stuff. Okay. Ties together the relation of the Taylor expansion to the curvature, second derivative to the circle, to the local curvature. And then when we do this derivative, just pure kinematics, we get b squared over r right there. Okay. That's a good one. Okay, that's all I've got for you today.